Hello friends, grab your coffee, grab your cookie, but today, keep both very far away from any nanomaterial lab or battery production line, because we are diving into some of the most advanced, unusual, and downright sneaky dusts in modern industry. I'm talking about ultra-fine dusts, engineered nanomaterials, carbon nanotubes, graphene dust, carbon fiber dust, aerogel particles, lithium-ion battery dust, catalyst powders, ceramic nanoparticles, and even dust from silicon chip manufacturing. This is the new frontier of industrial contamination, and I am Michael Klepik, your guide through this microscopic jungle. What these dusts really are. Technical description. These materials fall into three scientific families. First, ultrafine and nanoparticulate dusts, particles ranging from 1/1000th of a micron to 1 micron, extremely high surface area, extremely reactive, and capable of entering the deepest parts of the lungs. Second, carbon-based engineered nanomaterials, graphene, carbon nanotubes, carbon microfibers, and aerogel powders. These particles are conductive, strong, lightweight, and behave like airborne electrical wires. Third, advanced functional material dusts, lithium-ion battery powders, catalyst nanoparticles, ceramic submicron dust, silicon chip particulate, and photopolymer dusts. These powders are chemically complex, often toxic, and behave more like chemical reagents than simple dust. These dusts are not dust, they are engineered materials with engineered risks. Where these dusts are generated, you will find them in the most advanced industries in the world. Ultrafine dusts come from nanomaterial synthesis, powder drying, and research laboratories. Carbon nanotube and graphene dust appear during composite manufacturing, laser cutting, and additive manufacturing. Carbon fiber dust appears during trimming, sanding, grinding, and recycling of composites. Aerogel dust appears during insulation processing and material shaping. Lithium-ion battery dust appears during anode and cathode mixing, crushing of battery cells, and recycling lines. Catalyst dust appears in refinery catalysts, chemical processing, and metal oxide catalyst manufacturing. Ceramic nanopowder appears in sintering, powder metallurgy, and advanced coatings. Silicon chip dust appears in wafer cutting and polishing. Photopolymer dust appears in 3D printing and resin-based manufacturing. These are the dusts of the future, and they are already here. Why these dusts are dangerous to human health. Each behaves differently. Ultrafine dusts penetrate deep into the alveoli and enter the bloodstream. Carbon nanotubes behave like microscopic needles and can behave similarly to asbestos. Graphene dust irritates lungs and may cause oxidative stress. Carbon fiber dust causes mechanical irritation and respiratory inflammation. Aerogel dust produces severe dryness and mechanical abrasion inside the lungs. Lithium-ion battery dust contains nickel, cobalt, manganese, and reactive lithium salts. Catalyst dust may contain cobalt, nickel oxide, platinum, or vanadium. Ceramic nanoparticles produce lung scarring. Silicon chip dust often contains crystalline silica. Photopolymer dust is sensitizing and may cause long-term respiratory damage. These dusts are not safe at any concentration. Even tiny exposures matter. Combustibility and reactivity. These materials have diverse behaviors. Ultrafine dust is often explosible due to large surface area. Carbon nanotubes and graphene ignite easily and burn with high heat release. Carbon fiber fines are partially combustible and conductive. Aerogel dust is not combustible but extremely static active. Lithium-ion battery dust can self-heat, ignite with moisture, or generate flammable gas. Catalyst dust may catalyze unwanted reactions. Photopolymer dust can be combustible and UV reactive. Behavior in airflow. From an engineering perspective, ultrafine dust behaves like smoke and requires extremely high capture efficiency. Nanotubes and graphene stick to surfaces through electrostatic attraction. Carbon fibers travel in unpredictable aerodynamic paths, acting like microscopic threads. Aerogel dust floats indefinitely due to extremely low density. Lithium battery dust absorbs moisture, becomes sticky, and can self-heat inside ducts. Catalyst dust binds to duct walls and sensors. Ceramic nanopowders are abrasive and cut into filter membranes. This is the hardest group of dusts to control mechanically. Best filtration equipment for nanoscale dusts. Torch Air provides specialized systems. FOHN Nano Cartridge Collector for ultrafine and nanoparticulate sizes. FOHN HEPA Plus system for toxic metals like nickel, cobalt, and lithium salts. Blizzard Cleanroom Edition for semiconductor dust. Tornado Inert Bed Scrubber for reactive powders like lithium. Facet Ceramic Safe Cartridge System for abrasive ceramic nanopowders. Bora High Efficiency Extractor for 3D printing photopolymer dust. Nanoscale dust requires nanoscale filtration. OSHA, NFPA, and international compliance. These materials fall under multiple standards. Silica rule for silicon chip dust, OSHA 29 CFR 1910.1053. OSHA toxic metals for cobalt, nickel, and lithium-ion battery materials. NFPA combustible dust rules for carbon-based nanomaterials. NFPA 484 for reactive lithium, metal powders, and catalysts. Cleanroom ISO standards for semiconductor dust. These industries have some of the strictest air quality rules in the world. Dust collector system design. For nanomaterials and ultrafine dusts, I designed the system as a fully sealed, multi-stage engineered unit. First, differential pressure sensors with ultra-high sensitivity to detect minimal filter loading. Second, fully sealed negative pressure systems to prevent nanoparticle escape. Third, automatic discharge into stainless steel containers or sealed polymer liners. Fourth, HEPA or ULPA final filtration stages for submicron dust. Fifth, conductive ductwork and grounding for carbon-based nanomaterials. Sixth, explosion isolation for combustible nanopowders such as graphene and carbon nanotubes. Seventh, optional inert gas or oxygen reduction modules for lithium and reactive powders. This is high-precision engineering, not general-purpose dust control. Ultrafine dusts, carbon-based nanomaterials, lithium-ion powders, catalyst nanoparticles, ceramic nanodust, and photopolymer dusts represent the cutting edge of industrial hazards. They are small, reactive, combustible, toxic, aerodynamic, and almost impossible to control without advanced filtration technology. I am Michael Klepik. Protect your lungs, protect your equipment, and remember the future is nanoscale, but your safety system must be full scale. See you in the next video.